All right, let's talk about one of the absolute hottest techniques in AI right now, mixture of experts, or just MoE. You might have heard the term, and for good reason. It's basically the secret sauce that lets the biggest, most powerful AI models run incredibly fast. So, how on earth does it work?
Well, for a while now, AI researchers have been wrestling with this huge puzzle. To make an AI smarter, you generally have to make it bigger. More data, more parameters, but there's a catch. Bigger models are super slow and crazy expensive to run. So the question becomes, how do you get the raw power of a giant model, but with the speed of a small one? That is the exact problem that Mixture of Experts was born to solve.
Okay, so to really appreciate the solution, we first have to understand the problem. So let's start by looking at how things have traditionally been done, and why those older models kind of hit a wall.
Look at this comparison. On the left, you've got the old way, what we call a dense model. Think of it like one single massive brain where every single part of it has to light up and work on every single problem you throw at it. It's powerful, for sure, but it's also incredibly slow and inefficient. Now look to the right. That's the MoE model. This is more like a team of highly trained specialists. Instead of making everyone do all the work, you just call on the right expert for that specific task. The result? You get all that power, but with unbelievable efficiency.
So let's just nail down that term dense model. In a dense architecture, every single one of the model's parameters, you can think of that as its entire knowledge base, gets activated for every single calculation. The analogy of an overworked generalist is perfect. It's trying to be a world-class poet, a physicist, and a computer programmer all at the exact same time. And that right there is the core of the inefficiency problem.
So how do we fix it? Well, the solution is to break up that one-person show into a specialized team. And this team has two key players that you need to know about: the experts and the router.
First up, you have the experts. Now, these aren't experts in things like history or biology the way a human would be. In the AI world, each expert is actually its own smaller neural network that just gets really, really good at handling specific kinds of data patterns. A team of highly specialized consultants is a great way to think about it.
And of course, if the experts are your consultants, then the router is the brilliant project manager. Its only job is to look at every tiny piece of incoming data. We call these tokens, and instantly decide, okay, this one's a job for expert number 3 and expert number 7. Go. It's the traffic cop that directs everything and makes the whole system work. So here's how that flow works in practice. A piece of data, a token, comes in. The router immediately analyzes it and picks the best couple of experts for that specific job. Then, those experts get to work at the same time in parallel. Finally, their results are intelligently combined to create the final output. It's just a beautiful and incredibly efficient system. But just like with any team of people, you immediately run into some management challenges. How do you make sure the work is spread out fairly and that every expert actually gets a chance to learn and get better?
This is the big one. It's a huge problem when the model is training. If the router just finds 1 or 2 experts that are pretty good at their jobs and starts sending all the work to them, well, the other experts just sit on the sidelines. They never get a chance to practice, they never improve. You end up with 1 or 2 superstars and a whole bench of undertrained rookies.
So researchers came up with some really clever strategies to deal with this. One trick is to add a little bit of randomness to the router's decisions just to force it to give other experts a shot. Another uses something called an auxiliary loss, which is basically a penalty it gets during training if it doesn't spread the work out. And a third, and this one's really intuitive, is called expert capacity. You simply put a hard cap on how much work any single expert is allowed to take on.
And that capacity limit is super important. If the router's top pick for an expert is already busy, the token just gets sent to the next best choice. But what if all the good choices are at capacity? That's called an overflow. And in that case, the token just skips this step entirely and moves on. It's a trade-off, right? You gain a ton of efficiency, but you risk dropping a tiny bit of processing along the way.
Okay, that is enough theory for now. Let's look at how this all actually comes together in a real-world model that I'm pretty sure many of you have heard of, if not used. We are going to use Mixtral 8x7b as our case study. The name itself gives you a huge clue about its structure. That 8x means it has 8 distinct experts inside. So let's break down what that actually means for its performance. So when you go to download this model or load it onto a GPU, you need to have room for all 47 billion of its parameters. We call these the sparse parameters. It's the whole team, all the experts included, ready and waiting. That is a big model.
But here is the magic trick.
For any given task, for any single token you feed it, the model only actually uses about 13 billion of those parameters. These are the active parameters. So just think about that. You get the knowledge of a 47 billion parameter model, but with the speed and the cost of a much smaller 13 billion parameter model, that is an absolute game changer.
Let's just look at the breakdown here. You can see the shared parts of the model are always active, they're always on. But the experts, wow, they make up the vast majority of the model's size, 45 billion parameters. And yet, at any given moment, only a fraction of those are actually being used. That right there is the power of this architecture in a nutshell. And this powerful idea isn't just for language anymore. It's now starting to completely change the game for how AI systems see and interpret the world around them.
That's right, the same core concept, having a team of specialists managed by a smart router, is now being applied to computer vision, and it's unlocking whole new levels of performance and efficiency.
So instead of processing text tokens, a vision model will break an image up into a grid of little squares, or patches. The router then sends these patches to different vision experts. The main challenge, though, is that to keep things fast, the model often just has to drop the patches it thinks are less important. And of course, that means you're losing some information from the image.
So there are two ways to handle this. The standard Vision MoE, on the left, it makes a hard choice. Pick the most important patches and just throw the rest away. But on the right, there's a newer, more clever approach called Soft MoE. Instead of dropping patches, it actually blends them together into a combined, soft patch, making sure that information from the entire image gets used.
The key insight here is just brilliant. It's not about choosing which patches to send, it's about creating a smart, weighted blend of all the patches. It's such an elegant solution, and it completely prevents that information loss, which leads to much, much more accurate vision models.
So what's the big takeaway from all this? Simple. Mixture of Experts is a powerful design choice that lets us build AI models to absolutely enormous sizes. We're talking trillions of parameters, while keeping them fast and affordable enough to actually use. It really is the key that's unlocking the next generation of AI capabilities.
And that leaves us with a final thought. This idea of assembling the perfect specialized team on the fly is just so powerful. So beyond just language and vision, what other massive, complex problems in science and medicine and art could we solve if we could build the right team of digital experts for any task in a fraction of a second? The possibilities are just fascinating to think about.